Hello, Black Hat, and thank you for joining us on our talk on leveraging the Endpoint Security Framework for behavioral detections. I'm Jaron Bradley. I'm here presenting with my coworker, Matt Benyo. We both work at Jamf Threat Labs, where we focus on finding new ways to detect malicious activity on macOS devices. Over the past few years, this has meant leaning pretty heavily into the Apple Endpoint Security Framework, and today we wanted to share a bit about where we've found success with monitoring for applications that are behaving in ways that they shouldn't be.
So if you're here, there's a good chance that you probably know a thing or two about the Endpoint Security Framework. But regardless of your level of exposure, we're going to take a step back and put it into context. So what is the Endpoint Security Framework? So if you're building an endpoint security tool for an operating system, you really need two basic things. The first is a source of information about events that are happening in the operating system that feeds into your analysis and detections. And the second is the ability to act on detections, to exert authority. That could be killing a process or preventing a file from being deleted or modified and so on. And historically, the kernel, the heart of the operating system, is the place where we would go to access this data and exert this authority. So until recently, if you were developing an endpoint security tool for macOS, you'd build a kernel extension. And you had at your disposal to do so the OpenBSM audit trail for your event information. You had the KAuth kernel programming interface for your controls, which was a bit limited. And there's also the mandatory access control framework, which had the controls that vendors were looking for, but it was unsupported, undocumented, and ostensibly off limits to anyone but Apple. So the thing is, even by Apple's admission, kernel extensions are difficult to develop and maintain. And ultimately, they can create new security vulnerabilities because even a minor bug can lead to things like kernel panics. So these limitations really have served as a big obstacle to innovation in macOS security. So in an effort to secure their kernel, to give security vendors what they need to build tools, in 10.15, Apple introduced the Endpoint Security Framework. And in doing so, they are effectively serving up in user space an rich event information source and the controls to act on detections, all without adding any additional instability in the kernel. So instead of kernel extensions, vendors can now build system extensions that exist in user space. And the way this works is that when an event occurs, the kernel sends information to all of the third-party system extensions that are subscribed to a particular event. Things like process creates and exits, file creates, unlinks, mount events, that type of stuff. Most ESF events come in two different varieties. You have notification events and you have authorization events. They both deliver the same information, but notify events are simply meant to inform. So they let the system extension know that something's happened, and the system extension can use that information in whatever way it sees fit. Maybe it pops an alert to a console, or maybe it's forwarding data to a SIM. By contrast, authorization events actually hold up activity at the kernel. So the extension evaluates event data with its detection logic and determines whether this process should proceed. When an event fails the system extension checks, the system extension sends the deny response and the operation is terminated. Now, of course, this is just a visual representation for illustration, as the window for all this to occur is incredibly brief to maintain performance and user experience.
So static detections have been around since the early days of antivirus, and they continue to stick around because they're an effective means of detecting malware. Based on the way the auth events work, ESF complements static base blocking very nicely. While the execution of event is on hold, a third-party extension can quickly scan it, decide whether or not to allow it to execute. So what are some of the static behaviors that can be scanned in this small time window? Well, it can be a variety of things, but if we're going to prevent something, we better be really sure that it's not something that should be allowed to run, because once again, the last thing we want to do is ruin the user's macOS experience. So for this reason, traditional kind of indicators of compromise work really well. Team IDs or developers that have been identified as malicious in the past is an easy thing to quickly look up and block file hashes, file fingerprints of known malware. And then, of course, Yara rules work fantastic as well, allowing us to scan for byte patterns or strings and blocking if we see ones that we don't like. There's, of course, other options such as machine learning algorithms, but again, ultimately, whatever you end up testing against needs to return a result almost instantly.
So this leads naturally to the focus of our talk, which is behavioral detections. And this idea of a behavioral detection has been around for a while, and they've increased in value as security vendors have really refined developing a baseline of what normal application activity looks like as opposed to things that are more suspicious or nefarious. So the downside to this type of a detection is that they tend to have a higher false positive ratio because we're looking at a broader pattern of activity as opposed to something more objective like a file hash. But when these are executed correctly, it's a worthy trade-off because it allows us to identify things like malware that we haven't seen before or activity patterns that really haven't been seen before. So to give an example, we'll call this one a fake file extension, and we'll start with something really straightforward here. So in this example, a user goes to Finder in their temp directory, and they discover a PDF called a.pdf. Now, a single letter PDF in the temp file is probably weird enough to detect on its own, but we can take a closer look at this. And when they examine this file, they would discover that this is actually a macOS executable. So masquerading file extensions, using contradictory file extensions in this way is one of the oldest tricks in the book. Attackers will use this method to try and blend in with the user's files or the operating system. And somewhat ironically, these kind of cheap, evasive maneuvers lead to some of our best detections because they're hard to justify in a benign context.
So as you can see, all we really did here was take the behavior of a file being created or written to temp and perform some additional checks to determine if it was actually of any interest. So truth be told, like Benyo said, some of these might be interesting by themselves. For instance, a PDF extension on an executable is probably a detection by itself. But if we want to take additional kind of odd behaviors like, oh, this is in the temp directory, or this has a single letter file name. These are all just kind of strange things. And if we want to further kind of enhance and tighten up detections, we could look for multiple things like this to create one detection. We'll demonstrate a slightly more in-depth example of one of these detections with something we call plist disguised as Apple. So inside of the system library launch agents directory, a launch agent is something that will generally run at startup on the system when your system boots. And here we have what a launch agent should look like. This one belongs to the macOS diagnose agent. We actually tell this by simply looking at the file name. Apple encourages developers to follow suit and name all launch agents and daemons using a reverse domain name notation. So by looking at the file called com.apple.sysdiagnoseagent.plist, we should immediately know that this plist is part of the operating system and belongs to Apple. So a long time ago, malware authors caught on to this fact as well. So they began calling their malicious daemons and agents com.apple.fill-in-the-blank, causing those agents to blend in with the operating system as well. So if we look inside this file, we see that this agent will launch sysdiagnose helper. This executable is an Apple binary and properly signed by Apple, as it should be.
So let's take a look at how this can be counterfeited or abused by attackers. So what we'd be looking for is in the user launch agents or launch daemons directory, an addition of a new plist. That's the first thing we detect on. But then we look to see, are they using a com.apple identifier in the file name? And truth be told, we could stop right here. If there's something that's outside of the SIP-protected system launch agents directory, and it's in the users folder, that's probably suspicious enough to take a look at. But we have found some false positives that hit this. So we can refine this detection by doing some additional checks. So what we do is we look at that plist, and we scope in on the executable that this intends to run at login. And that's going to give us a path. So we can go to the executable at that path, and we can run a code signing check. And if this is something that's using a com.apple plist, we should hope or expect that this is an executable that's also owned by Apple. And in this case, the code signing information comes back as unsigned, and that is highly suspicious, something that we can confidently trigger a detection on for further analysis. So this has been a really reliable detection over the years. It is worth pointing out, though, that these days when we see this triggered, it's generally one of the newer espionage-focused applications. This is something that adware used to do a lot, but I think that they spend so much time in the trenches and they've been caught by so many different security products using this technique that's something that they've moved away from.
So far we've talked quite a bit about different behaviors and checks to perform with file activity. Let's get into a bit of background on what suspicious process activity looks like. So we're going to give an example here by showing off a single exec event. Let's say that you're maybe a threat hunter, you're in Splunk, and you encounter a process execution event. In this example, we're just demoing with a simple cut command. So for those that aren't familiar with the cut command, it's generally used to splice data passed to it from another command. By itself, it really tells us absolutely nothing. We're going to show here how we can use other fields in this event to get the context of what's happening on the system. So next, we'll use the parent process ID and grab the process that ran the cut command. It's primarily a tool meant to be used within a shell, so it comes as no surprise that the parent is ZSH in this case. Where we really start to gain some useful context here is when we take this same event and we look up the responsible PID, which in this case points to terminal.app. As we can see, this process ID starts to paint a better picture. So far, we've determined that the user opened a terminal, their shell of choice is the default, ZSH, and they executed cut. However, as I stated earlier, there's still more to this picture. And cut by itself isn't super helpful to us. But at least we know that this was likely a user because it was executed through a terminal GUI application. But by taking the process group ID value in this event, we can determine what the process group ID leader of this command was. This PID value is fairly well known, but it gets less attention than it deserves in threat hunting. Not only can we grab what process was at the front of a set of piped commands, in this case system profiler, but we can also perform a search to see all processes that share this same process group ID, essentially rebuilding the exact command that was executed. So this approach can't always be taken, as we're demoing an example here where standard job control behavior is in place. But overall, this is a pretty good way to go about getting the context of how a group of commands was executed. In this case, we can see that the executed command was one that gets used to grab a serial ID of the device it's run on. And it gets used by both legitimate apps and scripts, as well as some malware performing recon. A session is a collection of process groups, and a session ID points us to the process that's in control of those groups. And this is where we can kind of go and get some additional context of what actually ran inside the terminal. So in this case, it belongs to the login process, which the terminal runs upon execution before the shell is chosen. So from a single event that shows a simple cut command occurring, we were able to use all the PID fields to determine the exact context of what's happening. And then with some simple lookups, we can even sort out the command history that ran here in this terminal.
So let's take a look at an attack behavior that can be uncovered using some of these techniques that we just discussed. So in this particular demonstration, we're looking at a popular form of a living off the land technique. So in this technique, the attacker will host a script on their server, and they will curl that down on the victim machine, but pipe it directly to an interpreter on the system. And the reason that this is an attractive technique is because in doing so, no malicious files exist on the disk. Therefore, you can really sidestep most static detections this way, as the script really only exists in memory. Now, while this doesn't create files, it's not entirely untraceable. If you have that URL and the server's still up, you could go, for example, this is the Mythic agent that would be hosted on this server by Cody Thomas. That's still available, but you're creating that extra step and really going to sidestep any detections that aren't looking for this type of a technique specifically. So if we now look for Apple script, which is the interpreter in this case, being run, and we check for it in the process history, we'll see that it's running with no arguments. It's just running as OSA script. So to use ESF data to track this type of activity, what we would look for is the execution of the interpreter, in this case OSA script or Apple script. And if you look down below in the command, you would see that it has no path to a script, no additional commands, which is a pretty good giveaway that whatever is running the script was piped directly to the interpreter in this way. So the way that we can start to uncover this of what piped to OSA script is by looking at that process group ID. So if we follow that process group ID, we see that it leads us to the curl command. And once we have this link, we are confident that this type of a living off the land technique was being used, at least to the point of popping an alert for further analysis.
So let's walk through another sample that drives home the use case of, once again, the process group ID. Spotlight is functionality on macOS that indexes files and documents as they're created. It does this indexing by taking keywords found in those documents and making them easily findable in a search. So when you press Command and Spacebar, you can punch in a keyword and easily find the document you were looking for, even if you can't remember where you saved it. This is a super useful feature. I use it all the time, but any feature that's useful for us is generally also useful for an attacker. So mdfind is the command line equivalent of using this Spotlight functionality. So an attacker can easily search for different keywords in attempts to try and find files on the hard drive that contain these keywords, such as maybe password, routing an account, or confidential. So an attacker, once on the system, might use a command that looks something like this, where basically they run mdfind, they get a list of files back that contain the word confidential, and then they take each one of those files and pipe them immediately to an archive. And now they just have to exfil that archive, and they have a giant archive full of confidential files.
So in order to detect this happening, what we would look for is the execution of one of the built-in archive tools. In this example, it's tar. So then the next question is we ask, what is the process group ID of this tar execution? And in this case, following this process group ID would lead us naturally to mdfind. And when this link has been made, we can be reasonably confident that tar was run at a string of commands that started with mdfind, and this technique was likely being used to the point where we can pop an alert for further analysis. It's worth pointing out, though, that this technique, while interesting, is limited to what's available outside of the full disk aspect of the transparency, consent, and controls. There's still some useful things. We'll get a little bit more into TCC in one of our advanced detections.
So we've talked a bit about what we'd call standard detections. Now we'd like to get into some detections that require significantly more checks to determine applications behaving anonymously. All three detections we'll talk about here were developed after we discovered or learned about a zero-day vulnerability, and then we went and found a way to detect if those vulnerabilities were ever abused. So everything we'll cover here has since been patched. But we still wanted to make sure before those patches occurred that we were detecting them should it happen. So the first we're going to touch on is a Gatekeeper bypass from a while back. So a number of different bypasses have come to light over the course of this year revolving around file quarantine and Gatekeeper. These are both security features built into macOS that exist to help users ensure they're only running code that's properly been signed by a trusted developer and notarized. In this slide, we see that a user has downloaded and ran an app called toxic.app. This would result in this Gatekeeper prompt of something like this, primarily because the app is completely unsigned and therefore untrusted. So last year, Cedric Owens discovered a method that allowed apps to incorrectly pass Gatekeeper checks. He actually did a talk about this here at Black Hat. So we created a detection when we heard about this vulnerability and soon discovered a variant of the Schleyer malware abusing it in the wild. So before abusing this bypass, Schleyer developers had to convince you to override Gatekeeper because they didn't want to sign the malware. They would convince users to override Gatekeeper by literally providing instructions for the override process within their installer graphics. So this simply consists of right-clicking the application, selecting Open, rather than double-clicking on it. It seems very basic, but we see users fall for this all the time. We do see that this still results in some prompts informing the user that this app was downloaded from the internet, but ultimately they're given the option to go forward with it if they'd like to when right-clicking on the app. So that's what the old Schleyer malware installer looked like. Here's what the Schleyer malware with the Gatekeeper bypass embedded in it looked like. It's just a simple double-click on the downloaded application, and it's game over for the user. They didn't have to right-click the application nor click through various prompt warnings. This completely unsigned malware would execute and perform a bunch of background activities while the user was none the wiser. An additional note to make here is that although this looked like a PKG installer, it was actually just a weaponized application that used a PKG icon. But how did the bypass actually work? It worked in cases where an application did not contain an info.plist file, and it used a script as its primary payload. So if these two things were true, it would be given a stamp of approval from the Gatekeeper security check, and it would be allowed to execute.
So let's rewind a little bit and think about how we could actually detect this. So first of all, when an application is launched by double-clicking, it sends a message to launchd, which then goes on to open the application. So that's the thing that we would look for, is launchd being the parent process. Now, obviously, most of the processes that are running on the system have a parent of launchd, but by including this in the detection, we can reduce false positives. So our next check is to be checking to ensure that we're actually dealing with an application bundle. This can be done by analyzing the command line while the app was double-clicked. But what we can do very easily is look for this telltale string in the command line arguments of .app/contents/macOS. If we see this string, we're confident that we're dealing with an application. So next, we're going to ensure that the process that was running was actually a built-in interpreter. So what we did was we essentially looked for any of the built-in interpreters. At the time, there were a couple more that have since been deprecated, but these are all the ones that are available. And in the Schleyer example, it was actually Bash that was running. So the next thing we'll do is we want to make sure, since a requirement of this bypass was that the executable was a script, we'll look at the executable to ensure that it wasn't some type of a Mach-O binary, that it was actually a script. So you can do this via API, check magic bytes, whatever your particular flavor is. And then lastly, we want to make sure that we're catching this at the moment that it's being looked at by Gatekeeper. And for this, we relied on a particular quirk of Gatekeeper. So to mitigate a different vulnerability, when you double-click on an application that's in something like a DMG, Gatekeeper will actually move that to a randomized file path to prevent it from accessing external resources. And this particular feature is called app translocation. So that's what we'll look for to ensure that this is happening at the moment of a Gatekeeper inspection that will incorrectly pass checks.
So let's take a quick look at what all this looks like from an ESF perspective. Notice here that we can almost do all the checks required, once again, by pivoting around on a single exec event. So the first thing we're going to do is check that the parent is launchd. Next, we're going to take a look at the command line arguments and make sure a application is referenced within them. Instead of checking the command line arguments, we could also check the script field that ESF provides on execution. But in this case, we do see that the application is referenced inside the command line arguments. So next, we'll grab the path of the executable being exec'd to see if it matches an interpreter language, which in this case it does. We see that it's been Bash. And then we will take the application from the command line arguments and check to ensure that it's not a Mach-O, as, of course, for this bypass, we only care about scripts because that's all that worked. So finally, as mentioned before, we're going to check that this app is being analyzed by Gatekeeper, as we only want to trigger at the time that the Gatekeeper bypass is occurring. So you can actually use a script as your main payload in an application. Apple does allow for that, but when something like this happens, we want to trigger on this at the time of bypass. If the user still continues to want to run this in the future, that's up to them. So this is the detection we put into action when we heard the 0-day existed, and almost immediately as we pushed it out, we detected the Schleyer malware dropper triggering in various environments, which tells us malicious authors do see value in evading these Gatekeeper checks and do see value in not having to take the time to sign code or pay for any type of code signing fee. So next we're going to touch on a TCC bypass, which we hinted at a little bit earlier. As we showed earlier, TCC is kind of a feature where users can grant specific applications permissions to do specific things, such as capture keyboard input, record the mic, or record the screen. So when an application attempts to perform an action, such as record the screen, the user is prompted asking if they want to approve this action for the application. So perhaps one of the more concerning times where we've seen this prompt bypassed was in the wild by the XCS set malware. 0-day usage isn't new for this malware. In fact, it was using 2 other 0 days at the time as well. Specifically, we're going to focus in on the 0-day it would attempt to use in order to gain screen sharing permissions. The malware would start by looking for a list of various applications that already exist on the system and likely hold that screen recording permission. In the malware code, it referred to these applications as donor apps. Among these applications was, of course, Zoom, since at this point many users have had installed Zoom on their systems to remotely share their screens, and for that purpose it would have the screen sharing permission already. What the malware authors discovered is that if they placed an application bundle within an already existing application bundle, we'll call this update.app in this case, they could actually piggyback off the permissions that the existing bundle held. So if we go back to the TCC settings, this is effectively what would now be taking place. However, the piggybacking application would gain the permissions. It would gain the permissions, but it would not show up in this list of software as able to do so. So now all the attacker had to do was record the screen, and no prompts would be displayed to the user. I think an important takeaway here is that many don't think anyone's going to take the time on macOS to bypass these type of restrictions, when in fact, malware has already taken the time to try and find ways around this to remain more stealthy. This was all also done via Apple script malware, by the way, which some might argue makes this even more impressive.
So when this malware runs, it will trigger an Endpoint Security Framework exec event. And the way that we would detect this is to look for that application being opened. And we'd look at the path to first determine that we're dealing with an application. And the next thing we'll check is to see, is that application nested inside of another application? Now, keep in mind, Zoom is just the example here. In theory, it could be any application that had the desired TCC permissions. So now that we have an outer app and an inner application, we can start to treat those as 2 separate things. And it's worth pointing out that it's totally legal for developers to do this. It's a normal behavior to put one app inside of another application. However, we would expect that the signing information of those 2 applications would match. So that's how we were able to look for this being done illicitly. So we would check the donor application, give it a code signing check. In this case, it's the Zoom app. Surprise, surprise, it's signed by Zoom legitimately. So then next, we want to check the inner application, and we should expect that also to be signed by Zoom if this is a legitimate update app. And in the case of the XCS set malware, it came back as signed ad hoc, which was a huge red flag. So that's the detection. We're looking for an application being executed. We're looking for that application to be nested inside of another application. then we check the outer application signing information and see that it's legitimate. And for the inner application, when we check that signing information, if it's illegitimate, we'd see one of three cases: a mismatched team ID that doesn't match the outer app, signed ad hoc, or not signed at all. And if those conditions are met, we confidently pop an alert for further analysis. So let's talk about one last Gatekeeper bypass that we were able to detect. And this vulnerability was actually found by Jamf's own Firdaus Seljuki, and he was attributed on a CVE when this was patched by Apple. So to understand this particular bypass, we first have to quickly break down some of the basics of how Safari works. So when Safari is used to download a file, especially something like a zip file with an application in it, you may have noticed that it hits the downloads folder and is almost instantaneously unzipped. This is the default behavior. And this is part of a feature in Safari called Open Safe Files for downloading. It's what Apple deems safe files. And probably part of the thinking around this is something like an application, while it feels like a file, is actually a directory bundle and can't be downloaded directly. So often you'll see applications that are zipped up in this way, and using this auto unzip feature kind of abstracts that away so that it feels more logical to an end user.
So if we quickly rewind once again and then watch all of this in slow motion using the Endpoint Security Framework, what we would actually see is that after the archive download occurs through Safari, the Safari sandbox is actually what's responsible for creating a temporary directory and then handling the unzipping of that archive into that directory. So the Safari sandbox then takes the quarantine extended attribute and applies it to the newly unzipped application. This part's actually very important because when an application is opened for the first time, its extended attributes are checked by the system. If this quarantine extended attribute is on the opened application, the system knows that it needs to be checked by Gatekeeper upon its first launch. So while we were browsing the internet in search of malware, we encountered a gaming website that was hosting games in application form via zip archives. So after we downloaded these games, we noticed that they were somehow bypassing Gatekeeper's prompts despite being completely unsigned. So after further investigation, we actually noticed that the extended attribute was not being placed on the application directory itself. It was only being applied to the recursive contents under that app. And as it turns out, Gatekeeper only cares about whether that application has a quarantine mark on it or not. So we noticed that this wasn't actually happening if we downloaded the application via another browser and then unzipped it manually. All the quarantine attributes would appear as expected in this type of scenario. So this told us the issue lied somewhere in the Safari auto unzipper itself. Not only that, but we also noticed that if we used Apple's built-in ditto command to unzip our own archive, it would also result in the same quarantine bug. This told us the bug likely goes much deeper on the operating system somewhere, as it was affecting at least 2 different unarchiving technologies. So as it turned out, this issue existed within the bill of materials functionality. A bill of materials is, think of it like a receipt for all files that maybe an installer or archive leaves on the system. Logically, this receipt technology ties really well to PKG installers. However, macOS also builds and references a BOM for zip files as well. It's just not very well documented anywhere. So upon unarchiving the application from a normal zip file, the BOM, seen on the right here, will keep track of each file that gets unarchived. The unarchiving logic then goes through each file in the BOM and applies the quarantine attribute fittingly. So one big thing we noticed analyzing a normal zipped application in a hex editor is that the first zip file header starts at the root application directory. The quarantine attribute would always be applied as expected in this case, but the zip files we were downloading from the internet were unknowingly bypassing Gatekeeper, and on the other hand, they were missing this root level header. And instead, they started at the application's contents directory. So if we take one of these modified zip files and remove the top level header, we see here that when the BOM gets parsed, once again on the right. The application root directory would be missing from the bomb. However, the application would continue to unzip and operate normally. But when the copy quarantine function gets referenced, and it references the bill of materials to apply the quarantine attributes, it ends up missing the app directory itself, since the bill of materials at this point was out of sync.
So using the Endpoint Security Framework again as our foundation, how do we go about detecting this occurring? So we start by looking for a file rename event. We're looking for that moment when the Safari Sandbox broker is moving from its temp file, the new application, back to the downloads folder. Then we ensure that it's actually the Safari Sandbox broker that's taking the action. And then we make sure that it's actually an application that's in question that's being moved. Then we make sure that the original location is the temporary directory that the Sandbox broker creates when it's unzipping the file and moving it back to downloads. And then finally, we do an extended attribute lookup to ensure that the quarantine attribute was actually applied. So this detection is interesting because by looking over the shoulder of the built-in security and ensuring that it's doing its job as expected, we can generically detect when a gatekeeper bypass has occurred, even if we don't know what the technique is. All we're looking for is an application that's being downloaded by the Safari Sandbox broker and yet somehow came away without a quarantine attribute. And really, I think this highlights the beauty of these behavioral detections because they can allow us to pick up on techniques that we haven't even uncovered yet.
So that kind of wraps up our talk. What we showed today is simply one piece of tooling that feeds off events provided by the Endpoint Security Framework. But what's great about ESF is that Apple can focus on providing visibility into the operating system, and developers can get the power to decide what should be done with this information and build detections engines as well as anything else they can think of. More than anything, it's just nice to have these events that we use come from, that used to come from various complex sources, now be streamlined in an organized fashion from Apple, so we can focus on using the events rather than having to worry about creating them ourselves. And that's what we had. Thanks so much for having us.